Today I'm going to talk about deterministic sparse Fourier transform with an L-infinity guarantee. This is a joint work with Vasileios Nakos from Zalando University. Suppose that we have a signal x, which is an n-dimensional vector. Its Fourier transform, which we denote by x hat, is also an n-dimensional vector. Currently, the best algorithm to compute the Fourier transform of a vector is called the fast Fourier transform, which reads all the coordinates of x and runs in time O n log n, which is almost linear in n. The coordinates in the Fourier domain are also called frequencies. An important case is when x hat is sparse, that is, it has a few large frequencies and the rest are all small. We suppose that x hat is k-sparse, meaning that it has k-heavy frequencies, also called heavy hitters. Here in the picture, the gray level of cells denotes the magnitude of the frequencies, and we have k equals to 2 here, that is, x hat is 2 sparse. The goal of the Fourier sparse recovery problem is to find the heavy frequencies and their magnitudes. Hence, we wish to output an x hat prime, which is an approximation to the accurate x hat, and ideally should contain only the largest k frequencies. However, we do not restrict ourselves to output exactly k frequencies. Instead, we allow outputting slightly more frequencies, say big OK of them, as shown in the picture here. Since we only want to approximate the large frequencies, it is possible to read much fewer coordinates of the signal x than all n coordinates of it. And it's also possible to take only sublinear runtime in n, preferably k times polylog n. Note the number of entries we read is always upper bounded by the runtime. We know the number of entries we read, which are called samples, is also k times polylog n. The point here is that we want the runtime to have a linear dependence on k. If it's a polynomial dependence, we want the power to be as small as possible. We haven't defined what approximation means, so here are the definitions. So usually we consider two error metrics, the L2, L1 error metric and L-infinity L1 error metric. The left-hand side in both error metrics is x hat minus x hat prime, the approximation error measured in L2 or L-infinity norm. The right-hand side depends on x hat minus k, which is the vector of x hat after removing the largest k frequencies measured in the L1 norm. Note that the x hat minus k is the inevitable error. That is, even if we recover the largest k frequencies exactly, we are still left with this much error. And we also call x hat minus k the tail. And there's also another type of error where the right-hand side depends on the L2 norm of the tail instead of L1, and this is a stronger guarantee. So if we have an algorithm that gives L2 tail guarantees, then we automatically have an algorithm that gives us L1 error guarantee. For randomized algorithms, the best works have achieved both sample complexity and time complexity almost linear in k, up to log factors. However, there has also been lower bounds showing that to achieve the L2 norm of the tail on the right-hand side requires omega n samples, that is, reading essentially the entire vector. And here we want to read fewer than n coordinates of x, and so in this talk we only consider deterministic algorithms. Now we give a brief review on the previous results. We first remark that the L-infinity L1 is a stronger guarantee than L2 L1, which means if we have an L-infinity L1 algorithm, we can use it as a black box to construct an L2 L1 algorithm with similar sample complexity and time complexity. It's known that L2 L1 guarantee has a lower bound of omega k times log n over k samples. And the L-infinity L1 guarantee, being a stronger one, has a higher lower bound of omega k squared plus k log n samples. Note that the dependence on k becomes quadratic for L-infinity L1. Existing deterministic algorithms are for L2 L1. The best sample complexity is due to Havid and Regev in 2016. They achieved OK times log squared k times log n samples, optimal up to log factors, but the runtime is polynomial in n. The algorithm is actually to solve a linear program of size n. Another downside is that their construction is not explicit. They only showed there exists a deterministic choice of these many samples to recover the top k frequencies for any x. But it is not clear how to determine the positions of the samples in polynomial time in n. For sublinear time algorithms, the best result is due to Mahi et al. Achieving k-squared polylog n for both time and sample complexities, which is almost quadratically worse than the optimal bound. In this paper, we focus on the L-infinity of one error guarantee. We first give a superlinear time algorithm with linear dependence on n and k-squared log n samples. So the runtime is n times k log squared n. The number of samples is only suboptimal by 1 log n factor. Furthermore, the samples used by our algorithm is constructible in polynomial time. We also extend this algorithm to obtain a superlinear time algorithm at the cost of 1 more log factor in the number of samples. Our algorithm uses k squared log squared n samples and runs in time k squared log cubed n, completely dominating the result by Mahi et al. On the left. Closely related to the Fourier sparse recovery problem is a combinatorial object called incoherent matrices. In an incoherent matrix, each column has the unit length, and every two columns have inner product at most 1 over k. It is known that the incoherent matrix must have at least omega k squared log n over log k rows. When the incoherent matrix is a row subsampled DFT matrix, that is, each row of the incoherent matrix is a row in the discrete Fourier transform matrix, we can use the incoherent matrix to construct an L-infinity L1 algorithm. The resulting number of samples is proportional to the number of rows of the incoherent matrix, but the runtime has a linear dependence in n. Nearly tight deterministic constructions are known for general incoherent matrices, but nothing much was known in the subsampled DFT case. We give a construction of k squared log n rows, and the construction can be done in polynomial time. This gives another L-infinity of 1 algorithm with k squared log n samples. Next, we review the basic techniques, which have been used by all sublinear time Fourier sparse recovery algorithms. We want to hash the frequencies into buckets. Note that the hashing is done for the coordinates of x hat, but we only have access to the coordinates of x. The idea is to use kernels. Let G be an n-dimensional vector and G hat be its Fourier transform. The picture here plots G hat. Each color represents a bucket. Here G hat is 1 over an interval and 0 everywhere else. So if we take the inner product of G hat and X hat, we will be summing up the frequencies over the interval where G hat is 1. That interval corresponds to a bucket, and the bucket value is just the sum of everything falling in it. Now the question is, how do we compute this inner product by just accessing X? Since our kernel G hat is symmetric, the bucket value can be written as the convolution of G hat and X hat, which is the Fourier transform of the coordinate-wise product of G and X, and that we can compute. Remember, we are aiming at a sublinear time algorithm, so we need to be able to compute the coordinate-wise product of G and X very fast. This requires G to have a small support, usually of size k or k times log n. Since G is 0 outside an interval, G hat cannot be the same, and therefore we want G hat to approximate our ideal kernel. More specifically, we want G hat to have large plateau about 1 inside the bucket interval and take tiny values outside the bucket interval, as shown in the picture. When we take the inner product of x hat and such g hat, the result will only be bad if a large frequency falls in the transition region near the border of the bucket interval, where g hat falls sharply from almost 1 to almost 0. So far, a bucket interval is a block of consecutive frequencies. To simulate the usual hashing, we need to permute all frequencies in x hat, and then apply consecutive bucket intervals. In the Fourier domain, pseudo-random permutation I maps to AI plus B for random A and B can be easily implemented by scaling in the time domain. And if we hash all n frequencies into O of k buckets, we would expect the majority of the heavy hitters to land in different buckets. For a bucket containing the single heavy frequency, if the tail contribution to that bucket is small, the bucket value is a good approximation to the value of x hat at that frequency. Hence, the main question is to recover the index of the heavy frequency in each relevant bucket. This reduces our problem from k sparse x hat to 1 sparse x hat, and from k buckets to 1 bucket. Now we present our first algorithm, the one whose runtime has a linear dependence in n. As mentioned before, we hash all n frequencies into big O of k buckets, and then we repeat this random hash big O k times log n times independently. The key claim is that every two frequencies, whether they are heavy or not, are low correlated under bucketing in most repetitions. This low correlation ensures that the heavy frequencies are isolated in different buckets, and the contribution from the tail to the heavy bucket, that is bucket containing the heavy frequency, is small. As discussed before in this case, the bucket value is a good approximation to the heavy frequency, and we can then take the median of them. Here we need to know which frequency is heavy, so that we know which bucket it is hashed to in different repetitions. So we enumerate all n frequencies and obtain an estimate for each frequency, and thus the runtime has a linear dependence in n. Then we proceed as in an early paper of Indyk and Kapilov, that we recover all frequencies above a certain threshold, subtract what we recovered, and repeat with the residual. Here we increase the threshold over time, recovering heavy frequencies from small to large. For the proof of the claim, note that the low correlation between two frequencies gives an inequality on the hash function, and we want every two frequencies to have low correlation, so this reduces to n squared inequalities on the hash functions. Then we can show that those inequalities hold in expectation over the randomness of the pseudo permutation of the frequencies. Then we derandomized the standard argument of conditional expectation to obtain a deterministic construction of the hash functions, and this derandomization can be done in polynomial time. Now we improve the linear time algorithm to sublinear time. Remember, we need only to deal with the one sparse case. Suppose that I star is a large frequency, or x hat I star is large, and we want to recover the index of I star. The inverse Fourier transform allows us to write coordinate of x, say x beta, in terms of the Fourier coefficients x hat I, and this is the equation. The sum is over all n frequencies. We pull out I star from the sum, so we can write x beta equals to x hat I star times exponential plus the sum over I naught equal to I star. And since we assumed x hat I star is large, so the sum over I naught equal to I star looks like noise, and we can write it like this. This means that x beta is approximately x hat I star times the exponential. So if we look at the argument of x beta, it will be close to the argument of this dominating term here, that is, the argument of x hat I star plus 2 pi beta I star over n modulo 2 pi. But assuming that x hat I star is large enough, or the noise is small enough, we can estimate this argument modulo 2 pi up to a small constant, say pi over 8. So for beta equals to 0, we see that we obtain an estimate of argument of x hat I star up to pi over 8. Now for each beta not equal to 0, we can subtract off our estimate of argument x hat I star and obtain an estimate of 2 pi beta I star over n modulo 2 pi up to pi over 4. Moving beta around, we conclude that we can recover 2 pi I star over n modulo 2 pi up to pi over 4 beta. Let beta be 1. We know that 2 pi I star over n belongs to an arc of size pi over 4, as shown in the picture here. Next, let beta equal 2. We can estimate 2 pi I star over n modulo 2 pi up to pi over 8, but now there are two possible arcs containing 2 pi I star over n, and each arc had size pi over 8. Comparing the arc for beta equals to 1, we know that 2 pi I star over n belongs to the upper right arc. Next, let beta equal 4. We can estimate the angle up to pi over 16, but now there are 4 possible arcs. Comparing with the red one of size pi over 8, we know the true 2 pi I star over n belongs to the upper right arc again. Hence, each step we double beta and reduce by half the arc that contains 2 pi I star over n. In log n steps, we can pin down 2 pi I star over n up to pi over 2 to the n. That is, we can determine I star. This is a very simple algorithm, and it was a bit surprising to us that it did not appear in any literature before. Now we briefly discuss how we construct the incoherent matrix, which is rows upsampled matrix of the DFT matrix. Note that in the DFT matrix, all entries have the same magnitude, and that if we sample rows, the resulting matrix always has the same column norm. We just choose the rows randomly. We select each row with the same probability k squared log n over n, so that in the end we will have k squared log n rows in expectation. Here we use the indicator variable delta L to denote whether or not we select the nth row of the DFT matrix. Call the resulting submatrix B. Denote the ith column of B by Bi. The inner product of Bi and Bj is therefore the usual inner product of two columns of the DFT matrix, weighted by the indicator variables delta L, here as shown here, and here F denotes the DFT matrix. Now it is clear that the expectation of this inner product over delta L is 0, and FLI times FLJ's complex conjugate has constant magnitude, and hence we can apply Chernoff bound to both the real and imaginary parts separately and conclude a concentration inequality of the inner product. And similar to before, we can de-randomize via standard techniques, and here we need to delve into the arguments of the Chernoff bound. Another minor thing here is the number of total rows selected. We know that we will have k squared log n rows in expectation, and hence with high probability via Chernoff bound that we will have at most 2k squared log n rows, and this can be again made deterministic by a de-randomization argument, and we can further incorporate this de-randomization argument into the de-randomization for the inner product constraint above. In summary, we provide new bounds for the Fourier sparse recovery problem and the DFT incoherent matrices. We start with randomized constructions and make them deterministic via the randomization. Our constructions are explicit, meaning that they can be found in polynomial time. We have some additional minor results on incoherent matrices in the paper. One of them is a strongly explicit construction by exponential sum bounds such as Wales bound from number theory. If we have a better upper bound for certain exponential sums, we will have a better upper bound for incoherent matrices. The other result is the converse. We use the lower bound for the incoherent matrix to derive a slightly better lower bound for the exponential sum. And that's all. Thank you.